Hello? Hello? Okay. So, good afternoon, everybody. Welcome to the equality saturation session. And my name is Haobing Ni. I come from the University of Washington, and I will be serving as your session chair for this session. Okay, so we will get started in 2 minutes. And in this session, we have a total of 4 papers, which includes both new extensions to equality saturation engine itself and the new applications of applying the equality saturation technique to new domains. So I think it is very exciting to see both kinds of equality saturation research and see them go in hand. Okay, so let's get started. So for our first paper, I would like to recall everybody that the root of eGraphs lies in SMT solvers. And the application of SMT solvers require you to actually use lots of different versions of eGraphs because you want to explore the space of predicates and you want to try things and retreat back to things. So this paper really gets us back to this old root of eGraphs. And please, so welcome Jahrim, and he will explain how you can do that versioning very efficiently for eGraphs.
Thank you very much. This is joint work with my colleagues Zakhour, Pascal Weisenburger, and my supervisor Guido Salvaneschi. And in our group, we are interested in program verification. So you would consider a program like the following and prove some properties about it. This is going to be the running example. It's basically a function that is computing the distance between 2 points, given the difference between their coordinates, and some function f, which denotes which kind of distance we are interested in. And particularly, this function is going to perform some optimization depending on the inputs. So if, for example, x is equal to y, we are going to just apply f once. And now, when you're considering this kind of function, you might be interested in properties like, is the distance function actually commutative between x and y, given all these optimizations? And to do that, since this is an equational property, you're going to look at the program and see which equalities between terms hold. So first, you might look at the scope of the programs and notice that some equalities only hold under certain assumptions. For example, x is equal to y, but only in the first then branch, and in the else branch is actually different. And dx is equal to dy in the second then branch, and it's different in the other else branch. Right. So there are a lot of verification tools that are able to reason about these properties, and most of them rely on an SMT solvers. And the SMT solver itself will rely on a data structure which is called an eGraph, and inside of the eGraph is unified. More recently also, there are solvers that have been implemented directly on top of eGraphs, so automated prover like TESI and CCLemma, which are novel, and we also include those kind of solvers. So today I'm going to talk about union find and eGraphs and some extension to reason about conditions and more persistence. So first, let's deal with union finds. And a union find is really a way to encode an equivalence relation. It's basically a graph of nodes that are terms, and if 2 terms are connected, then they're equal. So we are going to consider the union find at point A in the program. And the way we're going to reason about equivalence relations here is we are going to put all the terms that we find in the programs inside the union find. So each term is a node. And now we're going to scan the program to see which equality actually holds. And in point A in the program, we start by saying that dx is equal to f of x. So the way we add this equality is by adding this edge between f of x and dx, and this is called a union, and operates as the root. And then you will discover dy is equal to f of y, and dx is equal to dy at point A in the program. Notably, the fact that the union only is only adding edges at roots. It means that actually the union find is not a graph, but it is a forest, and the forest is basically containing an equivalence class of terms. In this case, there is an equivalence class of 4 terms displayed. And moreover, since this equivalence class is a tree, it means that you can select a canonical element of the equivalence class by simply following the edges to the root. In this case, the equivalence class, or the representative of the equivalence class of f of y is dx. And finally, with path compression, you can shorten the path that you follow from the term so that future queries are going to be faster. So now there is a problem with this, with encoding equality in this way, at least like for each branch, and it's basically duplication. So if you were to consider a more complex program like this one, it doesn't matter really what it does, but it basically applies the distance function multiple times. And maybe we want to prove a property of this program, which is, or this function, which is some sort of commutativity of its arguments. Now, for example, we don't know what is AB, so we need to unfold the definition of this to understand what are the possible cases for AB to be. And we are going to see that the cases are the same as before, structured in the scopes. So we have to consider 3 cases. And I'm going to represent them as blue nodes on top of the green tree. And now, when you're going to unfold the second definition, you're going to span the same tree, but for each leaf, which means that you're going to now have to explore 9 cases. And if you keep going like this, you're going to reach exponential explosion. And more importantly, now you have to consider 81 cases, but there are a lot of ancestors in common between these cases, which means that there is a lot of redundant work that is shared. So we need to deal with this shared work, and this is why researching persistent techniques for union finds and egraph is very helpful. And this is, in fact, our first contribution, which is a version union find, which is a simple way to reason about persistent in union finds. So the first thing that we see is that the version union find has the same term space as a union find. So the terms in the graph are the same. But we now associate to each scope a version, which is some identifier, actually, just to recall that specific scope. So for example, x is equal to y in that scope, and that scope is called 0.1. And the idea is that equalities that hold at a certain scope must of course, hold also at inner scopes. And this is basically translated into descendant version are an equivalence relation that is a coarsening of equivalence relation of ancestor versions. So if you have this kind of structure, now you can scan the entire program. And the first thing that you will do is encounter x is equal to y, and you will just perform a union as before. But now you can also label the edge by saying that equality is actually only valid in the scope, 0.1. So now you can go along with the program, discover new equalities, and these are true, but in a different scope, 0.2. And those that are true in 0.1 are not true in 0.2. And when you find dx is equal to dy, this is an additional scope, which is 0.2.1. And now this union find is encoding all equivalence relations in the same data structure for these programs. Importantly, the equivalence is now basically an extension of connectivity, where you are allowed to follow edges that are either in the version you are querying or in an ancestor. So if you want to find the canonical, for example, of f of y at version 0.2.1, you are allowed to follow 0.2 because it's an ancestor, and 0.2.1 because it's the same version. So this traversal is allowed. And finally, you can also perform path compression by adding this additional edge. And this additional edge is not only shortening the path from the element to the other, to the representative, but it's also making it easier to recognize whether you can follow that edge or not, because you don't have to query whether it is an ancestor or not. Right. So there are a few problems with this, which first is to ensure correctness. That is, as I said, descendant version must coarsen ancestor versions. So I can construct an example like the following, where I'm unioning y and z as a descendant, and then y and x as an ancestor. And now what happens is that I have that x is equal to y at the ancestor, but not as the descendant anymore. So what I need to ensure is that every union at an ancestor actually implies unions as the descendants. So there is some process of propagation. And this propagation will add that additional edge, which ensure actually that x is equal to y as a descendant as well. And another problem with termination, which is actually related. And the problem is that I can construct an example where find doesn't terminate by adding this edge at a descendant. and this edge as the ancestor. And now if I were to query the equivalence class of y as a descendant version, I'm stuck into this loop. And the solution to this is somehow making these loops trivial to detect by maintaining version canonicals. So by propagation, I will end up with a configuration like the following, where I know that there is this self-loop around x, and now when the find traverses a self-loop, I know that I've reached the canonical for that specific query. And another way, one way to achieve this is by propagation as before, but another way is by full path compression, which achieves this different configuration, but it works all the same. So you can choose which optimization you want to do. Okay, we perform a complexity analysis of this data structure, and the idea is that we simulate a version union find using multiple copies of a union find. So we apply the same operation, but on multiple copies on union find, and in this way we can extend the classical result by Tarjan. And the basic idea is that the worst case for a version union find is the best case of maintaining that many clones, where that many means the number of versions that you're considering, which also means that any amount of propagation that you're avoiding, you're achieving better performances. And then when we reason about programs like this list function, we are also dealing with a function like that argument f. And if the functions are pure, then we have to deal with congruence, which basically means that we know that for equal input, a function must produce equal outputs. And the traditional way of doing this is using an E-graph. And the idea is that it's basically a union find where the elements are enode, and an enode is just a function application. And a function application is represented as a function symbol with some pointer to this argument. So for example, you can see the constant x is just the function symbol x applied to the null pointer, and the function application f of x is the function symbol f applied to x. Okay, so if we want to consider the E-graph at point B in the program, now you will discover the equality x is equal to y as before, and you can add it as in the union find. But now the problem is that you have just breaking the congruent invariance because you have equal input x and y, but different output f of x and f of y. So what you need to do is apply rebuilding. And rebuilding is really just unioning and finding. You want to union a node with its canonicalization, which is obtained by replacing its argument with canonicals. And this is a key insight because if rebuilding is just union and find, then we already have all the ingredients to have an version E-graph. And in fact, in a version E-graph, you would add this x is equal to y at a certain version, which is a labeled edge. And then if you want to restore congruence for that version, you're just going to apply the union and define as that version, and you will have the same correctness for the congruence invariant as that version. So if you're going to explore then the rest of the program, you're going to just proceed as a union find in this case, because that is the only case for congruence. So in the paper, we have several artifacts. The first one is a formalization where we define the union find and the E-graph, and we also prove them correct, where correctness means that a user would provide a sequence of equalities in certain versions, and the union find will represent the smallest reflexive, symmetric, and transitive closure of that sequence of equalities, and the E-graph is also the congruent closure. The version union find has also been mechanized in Lean. And the second artifact is an implementation, which is an open source library in Rust, where we support most common E-graph extensions like the fair rebuilding, E-class analysis, imaging, saturation, and extraction. And the insight is that most of them actually boil down into maintain some kind of version cache. Moreover, recently we explored version proof production, which is to appear as a paper actually in 2 weeks in Verel Getikub. So for the evaluation, we considered 3 case studies, and we compare 4 different approaches. The first one is versioned E-graph. The second one is a naive cloning of E-graphs. The third one is a naive implementation of persistent E-graph, which is basically using existing persistent data structure in Rust. And finally, Easter egg. In the first case study, we consider a parameter analysis where we vary some configuration of E-graphs, and we generate some random E-graphs. So it's a random workload. And we consider 25,000 configuration, and in general, for runtime and memory, we see that we achieve better performances. For the second case study, we consider an EOF solver, where the workload is push and pop, which means that we're going to only work on the leaves, and when we're done working on the leaves, we can also drop them. We consider 6,000 benchmarks from the SMT-lib about EOF theory, and we see that the performances are similar, maybe a bit better with respect to the best approach, which is the naive persistent egraph. And these are way better than the other two approaches. And finally, we consider another domain altogether, which is what I mentioned before, an automated prover called TESI by Singer 21. And this workload insistent concurrent, where the idea is that we want to explore the possibility of working at any version at any time. And we consider the 300 benchmarks from the original paper. And here we perform similar to the best approach, which is cloning, which is way better than the other two. So for the parameter analysis, since I could not pick some precise measurement, I'm going to show the charts. And in the charts, we can see basically on the y-axis the resources for generating a certain configuration in terms of time or memory. And on the x-axis, the number of nodes and unions. We also varied the versions, but I cannot show it in the presentation. So what we see is basically that lower means better, and version egraph is consistently better in terms of time and memory, varying unions and unions. Right, so just to wrap up, in summary, we are interested in program verification, so we are going to consider some programs, and we want to prove some properties about them. And to do that, we are going to deal with equalities, and some of these equalities will all only under certain assumptions. Then we provided a new implementation of persistence for union find and egraph, which basically aims to reduce the amount of redundant work between equalities that hold under different assumptions. And then we provide a formalization to prove the correctness of the version union find and egraph, and open source library with most common egraph extensions. And finally, an evaluation of 3 case studies where we show that we are either better or comparable to the best approach in the state of the art. So if you are interested in looking at the paper, where there will be many more details, you can scan the QR code. You can also find on the top right a link to the artifact and to a Jupyter notebook where there is an easy implementation where you can try it out. So thanks for the attention, and I'm open for questions.
Okay. Thanks, Jahrim. And now it's time for questions.
Hello, I'm Adam Chapala from MIT. My understanding of kind of the API of your system is that it lets you track logical consequences in multiple different hypothesis contexts at once, and takes advantage of implication relationships across those hypothesis contexts. But it seems like the only implications you use are those that are present syntactically in the program that you're verifying. And there could be other provable implications, maybe even some that only follow using information deduced through equality saturation that you're not taking advantage of. Does that sound fair?
I see your point. So I guess what you're saying is something like you might discover that some condition might actually be the same, and maybe you want to share equalities between those conditions, right?
A really basic example would be you just copy and paste 2 versions of a program in a row, and you want to reuse all the work from analysis of the first one for analysis of the second one.
Yeah. I think like I had an idea where you would be able to, actually this is kind of future work, where I wanted the ability to be able to merge 2 versions in such a way that you do not only share among scopes, but also among independent versions that somehow, for some semantic reason, you know that they share something, right? So this is a bit forward-looking, though, like it's work in progress.
Sounds like a great extension to look at. Thank you.
Okay.
Hey, thanks for the good talk. Max Wilsey from UC Berkeley. Do the versions have to form a tree? Do the versions have to form a tree, or can they be just partially ordered?
Yeah, it's part of this actually. Like right now they are only a tree, but potentially what you could do is, for example, say that you want to union two versions, and you want to consider a new version that is actually inheriting from two, or maybe intersecting two versions, saying, for example, if you want to do a case analysis, you want to only consider facts that hold in any of them, right? In all of them, sorry.
But currently they're just a tree.
Yeah.
Okay, cool.
Okay, I think we can have.
Thanks, great talk. So it seems so this work is solving the same problem as a color graph, but it seems yours is better. Is that true? And could you give the intuition for why it's better?
Why it is better? Yes, I can give some observations about what are the differences between other approaches. If I can, it's lagging a bit, sorry. Right, so these are some of the features basically of version eGraph. The idea that we have full sharing between the term space across versions. There is also partial sharing of equalities between dependent version, and this is kind of the scope. And the idea is that right now it's between dependent version, but we want to do it, as I said, between independent versions. Then there is this version path compression, which is actually trading off memory with runtime. So there is a better balance. Also, since you have a view about all the versions that you're maintaining, you can also do better cache management. For example, if you apply equality saturation at a version, maybe you need the cache for that version, but you don't need for another version that you're not considering at the moment, right? Yeah, a bit of the cons is that right now the implementation of this eGraph extension is very naive, and we should probably look into some more version-aware extensions. And yes, of course, it is a bit more complex to achieve parallelism with respect to cloning or simple persistence.
Okay, let's thank Jahrim again.